Hi, we're going to write a cover for the dyadic iota or index of primitive in APL, which behaves exactly like the original, except one thing. So when we use dyadic iota to look up things from the right argument in the collection, that's the left argument, and what we're looking for isn't found, it will give the next index after the last position to indicate that something is not found. This is a really useful behavior because it allows us to take indices where things are found and use those to index into another substitution collection. So we can do a mapping from one thing to another, and then we can add another element at the end, which all missing elements will be mapped to. But the problem here is to change that behavior. So instead of getting the next index after the last element, we are getting a 0, which only makes sense when you're using one-based indexing, which is what APL does by default, because that means that 0 will also be a unique result. It will indicate an element before the first one instead of after the last one. And there are a couple of different ways that we can do this. Let's first look at just the normal behavior. So here we've got the dyadic iota. We have character vectors, and we can see that the A was found at position 3, that's this one, and then there are 6 letters on the left. We're looking for P, there aren't any, so we are indicating position 7, and then position 4 for the L over here. Okay, so there are a couple of different ways that we could approach this, and one of the ways is to simply check whether or not the index that we get is larger than the length of the left argument. So we can do this if we say that the index that we got is larger than the length of the left argument. And then we can use this to map the 7 to a 0. So an easy way to do it would be using multiplication, but then it's doing the wrong thing because we're multiplying the 3 and the 4 here with zeros. If we instead invert this conditional, so instead of being greater than, then not greater than, that's the same thing as less than or equal to. And then we can take this and multiply it with the indices themselves over here. So this goes from the right to left. It binds like this. That is the length of the left argument. And then we have the index. And then we have the comparison. And then we multiply that with the index itself. And that gives us a result that we want. However, there's a bit of an inefficiency here in that we're actually finding the indices twice. And we can fix that in various ways. One of the ways would be to take a new function that takes as arguments the indices and the length of the left argument, which are all the data we need. We don't actually need access to our original arguments, and apply a function to those. So here we have the indices and the length of the left argument, and then we want to have the same formula as we had above, but instead of taking the indices and the length of the left argument, we can just refer to those arguments. So here, less than or equal to, that is applied between these two arguments, and then we multiply by the left argument. So this is one way it could be written. We could also have passed in the left argument directly, and then we could have, this would still refer to the indices, then we could have compared the indices which come from the left with the length of the right argument. That means we would want to take this function and apply it between these two arguments, which is the left argument and the indices, but pre-processing the right argument to the comparison function with the length. So we can do that as follows, and that will still work. A whole different way to do it is to post-process the indices that we get. So essentially what we want to do here is we want to wrap around. When we hit the limit, which is the length of the left argument, then we want to wrap around to 0. And this is exactly what modulus or division remainder does. So if we take the indices and then we want to wrap around where the cutoff is 1 more than the length of the left argument. So we could write that in a tacit form, 1 plus the length of the left argument, and this would still work. We could also eliminate this parenthesis by swapping the argument of the modulus function. So this operator modifies this function such that it takes the arguments in reversed order, and then we take the indices like that. Another way to do it is to simply define this as an explicit function, and that might actually read nicer, and it's no longer. So these are some good solutions to the problem. Thank you for watching.